In the case of a finite life, we are able to calculate the life of a component if we know the alternating stress in the case of completely reverse stress. Now, in that case, we have taken the one component and is subjected to one type of loading. So in practical situation, the same component may be subjected to different number of loading at different cycles. For that one, you have to consider the damage accumulation method, which one is given by minus rule. So we'll study here the minus rule. For this one, we'll consider here a ascent diagram for completely reverse stress, in which we have mean value of the stress will be equal to 0 and the amplitude stress will be same as equal to the maximum stress. For a given material here, the knee point is formed at 5 into 10 to the power 5. So the corresponding value here will be the SE value, which is very close to 600 megapascal. So this value represent here the SE value, that is the endurance limit. So 5 into 10 to the power 5 corresponds here the infinite life, and lower than 5 into 10 to the power 5 we have a finite life. So this range represents here the finite life, which is less than 5 into 10 to the power 5. This is true when we have alternating stress sigma A is greater than the value of SE. So if we have sigma A is greater than endurance strength, in that case the life will be finite, and we can calculate this life using the Basquin equation, which one is given as amplitude stress is equal to constant A into number of cycle to the power B. A value we can calculate as SM square divided by SE, and the value of B we can calculate as minus 1 by 3 log of SM, that is the material strength, which is equal to 0.9 of SUT in case of bending, divided by endurance strength, and you have to take the log to the base 10. So using the value of sigma A, we are able to calculate here what will the life here N. Now this plot already I have given you, so you have to just record the value here. This time we have endurance strength SE is very close to about 550 megapascal, lower than 620. So let's say approximately we have 600 megapascal is the value of endurance strength. So for amplitude stress of 830, that is at this point here, we have a life is equal to 5 into 10 to the power 4, which is less than the infinite life. So this value already I have recorded using the graph. So there is no need for calculation. You have to just read this value. Approximately at 10 to the power 5, we have the amplitude stress will be lower than 830 but greater than 690. That is 830 to 700. So it is very close to this point here, which is approximately equal to 740 or 730 megapascal. At endurance limit here, that is at this point C here, endurance strength is 600 megapascal and the life is supposed to be infinite. If we have a stress level less than the endurance, that is a sigma A is less than SE, that is 550 480, which is less than 600, then we have the life is infinite. So this life is called as the infinite life. To demonstrate here the damage accumulation for different cycle, I will take the example of this material whose SN curve is as shown in figure. So the basic principle of the damage accumulation is based on the assumption that any given level of a stress applied for one cycle loading contribute a certain amount of damage to the component. Suppose we select here the point A, and the life of the cycle is 5 into 10 to the power 4, and suppose we operate the component which will produce the alternating stress equal to 830 for 100 cycle. Then the damage part will be equal to 100 divided by 5 into 10 to the power 4. That much fraction of the damage will be done at point A. Second point we'll consider either at here or either at SE or lower than SE, that is for infinite life. Then there is a accumulation. Whatever this total accumulation of a damage is there will be calculated using the minus rule. Suppose we consider the point A on ascent diagram. For this one we have a stress is equal to 830 and the corresponding life is given as 5 into 10 to the power 4. So machine part developing a alternating stress equal to 830 megapascal has a life of n1 is equal to 5 into 10 to the power 4 cycle. Under this condition, suppose the specimen experiences alpha 1 is equal to 100 cycle at this stress level of 830 megapascal. Then we can calculate here the damage accounting for stress amplitude equal to 830, and that damage ratio we can calculate as alpha 1 by n1 is 100 divided by 5 into 10 to the power 4. Likewise, we can consider here all the points on this diagram on which the specimen is used. Now consider here the point B. At this point also the specimen is operated for a certain number of cycle. So at this point we have approximately the stress is equal to 650. It is slightly less than 690 and greater than 620. So we can very well locate a amplitude stress equal to 650 megapascal on this graph, and we can record the corresponding value, that is the life of component is 2 into 10 to the power 5. Suppose this specimen is experiencing alpha 2 number of cycles is equal to 1500 cycles at the given stress level of 650 megapascal. Then again we can calculate here the damage amounting to the ratio alpha 2 by n2. This time we are operating the specimen at 650 megapascal for 1500 cycle. So corresponding damage will be equal to alpha 2 by n2 is equal to 1500 divided by 2 into 10 to the power 5. Likewise, we have given here one set of a stress where the components are given, and we have given the value of alpha 1, alpha 2, alpha 3, sigma a1, sigma a2, sigma a3. Corresponding number of cycle for finite part we can calculate using the Baskin equation, like the value of n1, n2, n3. Then we are able to calculate what is the total damage and what is the life of a component if it will undergo different number of cycles at a different stress level having different number of lives. That rule is called as minor rule. At the knee point we have a endurance strength, and this value of endurance strength approximately is equal to 600 megapascal. And if the operating condition of a specimen is such that the amplitude stress is less than 600 megapascal, that is the endurance limit, then the component has an infinite limit, because this one is a knee point. Suppose we operate an alternate stress equal to 520. This value of 520 is less than the endurance strength of 600, and therefore we are find here the life will be the infinite life. We are not able to locate the point because it comes under the infinite life. Infinite life means that we have to take the value of n equal to infinity. So if you are operating a specimen for a alternating stress which is less than AC, then the part will not produce any type of damage because the alternating stress is less than the endurance strength. In that case, the ratio will be equal to alpha 3 divided by n, which will be equal to infinity. So in this case, if I say the life will be equal to infinity, and therefore it is alpha 3 by n3, that is alpha 3 by infinity equal to 0. So these are the situations where we have given the value of amplitude stress, corresponding value of alpha. Using the Baskin equation we can calculate n1. Now same process we can repeat if we have given the another value of amplitude stress and the corresponding value of alpha 2. And if your amplitude stress is less than endurance strength, then its contribution will be equal to 0. So we add here all damages, that is alpha 1 by n1, alpha 2 by n2 plus alpha 3 by n3. That will be the total damage. And if this total damage is equal to 1, in that case we can equate the total damage equal to 1 by n, and using the value of n we can calculate here what is the total life of a specimen if we'll undergo the different type of alternating stresses for different number of cycles. So again repeat here that if we consider the point A and we have endurance strength here is equal to 600. Now you have to check here the amplitude stress. If the amplitude stress is more than endurance strength, in that case we have a finite life. Suppose on the graph we read this value n1 equal to 5 into 10 to the power 4, and this specimen is operated for alpha 1 number of cycle, then the damage ratio we can calculate as alpha 1 by n1. Secondly, if the same component has an alternating stress equal to 650 operated for 1200 number of cycle, then we have damage ratio equal to alpha 2 by n2. This n1, n2 you have to calculate when the amplitude stress is greater than the endurance strength. But if the amplitude stress is less than endurance strength, then the life is infinite and the value of n will be equal to infinity. So in this case, alpha 3 by n3 will be equal to 0. So all this sum here of a damage, that is alpha 1 by n1 plus alpha 2 by n2, likewise if you add all this value up to alpha n divided by nn, and you equate this value of alpha divided by n, and suppose this value of alpha is equal to 1, then you can calculate here the life of a component which undergo for different stress levels for different number of cycle. So the total life of a component subject to a sequence of loading levels, if alpha I represent here the number of cycle of a specific stress level sigma ai, and ni represent here the life of the cycle which you can calculate using the Baskin equation, and when the several stress levels are experienced for different number of cycles from I is equal to 1 to I is equal to n, then we can calculate here the cumulative damage. This cumulative damage is given as summation of alpha I by ni, that is alpha 1 by n1 plus alpha 2 by n2 plus alpha 3 by n3. Then the failure is predicted when dc is equal to 1, and in that case if I equate the value of cumulative damage equal to 1 by n, I can calculate here the number of life of a component which is subjected to sequence loading levels. This one is called as minor rule. In fact, here the constant is c, and this constant c is taken as approximately equal to 0.7 less than equal to the constant c less than equal to 2.2. In our situation, we'll select the constant equal to 1 and we'll find out the given equation, that is the value of alpha 1 n1 plus alpha 2 n2 plus alpha 3 n3 is equal to 1 by n, and we can calculate here the life of a component. So as far as we are considered and we have to find out the component life, in that case we have to just equate the value of alpha 1 by n1 plus alpha 2 by n2 plus alpha 3 by n3 is equal to 1 divided by n, assuming that alpha 1 plus alpha 2 plus alpha 3, this one is basically fraction, we have to take is equal to 1. They can claim the value of alpha 1 not in terms of cycle. They will say the total cycle time is t, in that case 0.85 times of t will be the alpha 1, and it goes for the stress equal to sigma a1, then 0.1 times t is alpha 2 and 0.05 times of t, that is equal to total t. So this time the value is balanced. So they can give in the terms of number of cycle, or they can give you as a percentage of time the component is experiencing a amplitude stress equal to sigma a1, sigma a2, sigma a3. The work cycle of a mechanical component subjected to completely reverse bending stresses contains the following three elements. First, we have amplitude stress is equal to 350 megapascal for 85% of time. So we have sigma a1 is equal to 350 and alpha 1 equal to 0.85. Then we have plus minus 400. So amplitude stress will be equal to 400 megapascal and 12% of time. So alpha 2 is equal to 0.12. And third case, we have 500 megapascal plus minus. So amplitude stress will be same as 500. And 3% means alpha 3 equal to 0.03. 3% plus 12% is 15% plus 85. It means that we have alpha 1 plus alpha 2 plus alpha 3 is equal to 1. The material for the component is 50 C4, for which SUT is equal to 660 Newton per mm square. The corrected endurance limit AC is given as 280, and all these stresses 350, 400 and 500 are greater than the endurance strength, and therefore they have a finite life. We can calculate here the finite life using the Baskin equation, and we have given here the bending stress. So from SUT we can calculate here the material strength, and using the endurance strength we'll first calculate the constant A and B used in the Baskin equation. So first of all, we'll do the calculation of a constant in the Baskin equation. We have given the value of SUT, which is equal to 660 megapascal. In case of bending, we have material strength SM will be taken as 0.9 of SUT. That is, we have 0.9 of SUT is equal to 660, which is equal to 594 megapascal. And we have endurance strength. So value of SM and endurance strength will not change. And we have given the value of endurance strength equal to 280 megapascal. The Baskin equation is given as the amplitude stress sigma A is equal to a constant A multiplied by number of cycle and the power is equal to B. If you recall here, the constant A is simply equal to Sm square divided by endurance strength. We have material strength equal to 594. We have to make a square of it, and we have endurance strength equal to 280. So in this case, we get a constant A equal to 1260. Second constant B we can calculate as minus 1 by 3 into log of base 10 is Sm by Se is same as equal to minus 1 by 3 into log base is 10, material strength is 594 and endurance strength is equal to 280. If you solve this, you will get this constant is minus 0.1089. Now one by one we will collect the data here, and we will check here that a value of 350, 400 and 500 all are greater than AC, so they have a finite life. And from this equation we can solve for life, that is the number of cycle equal to sigma A divided by A and the power is 1 by B. So this information I will solve in the form of table. First column we will make for the amplitude stress, that is 350, 400 and 500. Second column will make for alpha 1 is 0.85, alpha 2 is equal to 0.12, alpha 3 is equal to 0.3. Using the Baskin equation we can calculate N1, N2, N3. So I will just make ready this equation here. We have sigma amplitude is divided by the constant A, which is 1260, and whole power is basically it's a minus 1 divided by 0.1089. So let's put here 1 by 1 value. First case we have sigma amplitude is equal to 350. Corresponding value of alpha 1 will be equal to 0.85. You have to substitute in this equation, you have to calculate N1 and record this value is very close to 128797. Then we have to substitute for sigma A2. We have sigma A2 is equal to 400, alpha 2 is equal to 12%, 12% is 0.12, and then again use the same equation. Constant A and B will not change because they are dependent on Sm and AC. So endurance strength and the material strength will not change, so they have to use the same constant. Solve it, you will get this answer close to 37780. Next we have to use the sigma A3, that is equal to 500. Actually this time the life is very less. It is operating for alpha 3 is equal to 3% is 0.03. Substitute again in the same equation and calculate the value of N3. This time you will get the number of cycle is very small, is 4866. So in this fashion you have to make ready all the calculation N1, N2, N3, alpha 1, alpha 2, alpha 3, and now you can apply the minor rule. One cross check we will do here. We getting this value of alpha is equal to 0.85 plus 0.15 is equal to 1. So by minor rule we have alpha divided by n is equal to alpha 1 by n1 plus alpha 2 by n2 plus alpha 3 by n3. So n represent here the life of the component. Alpha is equal to 1, so we have 1 divided by n, alpha 1 you have to substitute as 0.85, so we have 0.85. Correspondingly you have to divide it by number of cycle n1, which one is 128797, plus alpha 2 is equal to 0.12 divided by n2. n2 is equal to 37780, plus alpha 3 equal to 0.03 divided by n3, which is 4866. Solve this equation. Naturally this will take a time here to solve for n1 and 2 n3. So if you solve it, you will get the value of n is very close to 62723. so this is approximate answer I am giving you. Your value will be plus minus 62723 cycles. But naturally this is very time consuming technique, so just I will introduce you what is the minus rule, how to calculate the cumulative damage if it is subjected to different type of alternating stresses for different number of cycles. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.